All right, we're going to start chapter 10 today. This is going to be, we're going to be moving from kind of the more theoretical treatment of shear forces and boundary layers in chapter 9 to the more practical application of in fluid mechanics of flow and conduits. And so this should be a little bit more practical from an engineering point of view. And so our roadmap is to explain how to analyze flow and conduits. We're going to use the energy equation primarily in Chapter 7. And this is going to expand our knowledge on how to calculate head loss, as I've mentioned before. And in addition, this chapter explains how to design pipes into systems and how to analyze a network of pipes. So it's quite a practical chapter. This particular section or recording is going to be just the first two sections on classifying flow in a conduit as either laminar or turbulent. And basically, we're going to set the Reynolds number, some limits on the Reynolds number for these for conduits. And we're also going to introduce a new concept called developing flow or fully developed flow, and we're going to classify flow into these two categories. And then just briefly, we will talk about specifying pipe sizes using the NPS standard in section 2. That's a very brief section, so I'm just adding it on to the end of this. So let's get going. So a conduit is any pipe or tube or a duct that is completely filled with a flowing fluid. So this could be a water pipe, for instance, or perhaps an air duct. So any closed system here. And the other thing about conduits is in this chapter is that they're going to be completely filled with fluid. In order to calculate head loss, we're going to need to make two decisions about the flow. We need to determine if it's laminar or turbulent, and to do this, we're going to use what's called the Reynolds number, which we've talked about before, and we will see that it will be applied to the diameter of the conduit, and whether it's fully or developing or fully developed, and we will be using something called the entrance length, L sub E, to specify the length along the conduit at which the flow is developing, and then after that length is achieved, the flow will be fully developed. So what the first decision of whether or not flow is laminar or turbulent is really decided based on the Reynolds number. And as we've talked about before, Reynolds did some experiments. He was an experimentalist who did a lot of fluid mechanical experiments. And this was an example or just a picture of his apparatus that he used. And so what he was doing was he was injecting fluid into a glass tube, but also had some dye in there. And he was doing various experiments. For instance, if he had laminar flow at certain flow velocities, he would just get a nice long streamline, similar to the video that we watched on streamlines and streak lines before. And he noticed that if he disturbed the flow somehow, or if he sped up the velocity of the flow, he could get the development of turbulence and then a fully developed turbulent flow with eddies in it. And he devised various ingenious ways to measure these properties of a fluid in his experimental setup. And so really this just boils down to the fact that in a conduit, we have these limits. It's really that simple, that in a conduit, if the Reynolds number applied to the diameter of the conduit, in the case of pipes, this D is the characteristic length of the conduit, and obviously for a pipe, we're talking about D being the diameter of the pipe. But in any case, very simple limits. If the Reynolds number for the conduit is less than or equal to 2,000, we have laminar flow. If it's between 2,000 and 3,000, it's unpredictable, and you should be remembering that this is in the transition region. This would be the transition region where we're going between laminar and turbulent flow, and then when we have a Reynolds number that's greater than 3,000, we have turbulent flow. Now, note that they're using 2 and 3,000 the same in these equations, so it's probably reasonable to say if the flow is actually less than 2,000 or greater than 3,000. That way, it's a bit. It doesn't include 2,000 in more than one of these inequalities. So this was a mistake in the book, but you get the idea. Okay, and so it's very easy to determine laminar versus turbulent flow. Now, what do we mean by developing or fully developed flow? This is for instance, let's take the example of say a large reservoir entering into a large conduit, maybe an outflow pipe here. There's going to be a certain distance that the flow encounters where the velocity profile is developing into a steady or a uniform velocity profile. And in this case, the wall shear stress is changing, and it's changing as the velocity profile changes. So we're in this part of the flow, in this pipe, this conduit, where the velocity profile is changing as a result of the shear stresses. So in this length here, from here's the entrance length, LE, during this or along this length of the pipe, we are in the developing flow regime, where the velocity profile is changing, and we can see that the wall shear stress is decreasing. Once it reaches a constant value, the velocity profile is uniform and steady, potentially until it becomes turbulent, and we have a fully developed flow in the pipe. And we have some equations here for calculating the entrance length, and this is going to specify the length along the pipe for the flow to become fully developed, and it's easy to calculate. However, it's important to note that we do beforehand need to know what the Reynolds number is, because we're going to apply the Reynolds number, or the entrance length. We're going to apply a different equation for laminar flow than turbulent flow. So it's going to depend on really the initial velocity here, or the velocity in the pipe, whether it's flow, turbulent, or laminar. So we have a way of classifying between laminar and turbulent using these equations here, and we have a way of calculating the entrance length to determine whether we're in a part of the pipe that's developing flow or fully developed flow. So we have these 4 categories. We can have laminar developing if we're within the if we're along the tube less than the entrance length. And once we're beyond the entrance length, we will be laminar fully developed if we're in the laminar region. If we're in the turbulent region, we can also have developing a fully developed flow, but we obviously will use this equation here to calculate the value. As I mentioned before, we'll need to first calculate the Reynolds number to determine which situation we're in. So we'll do some examples like this in class during our time to work out problems. The final thing I want to say is that we need to have a way of specifying pipe sizes. You could see how, since the Reynolds number depends on, let me just also state what the Reynolds number is. Go back. I did not write this down, but as usual, the Reynolds number is going to be the velocity times the diameter over the kinematic viscosity. Or there's a number of ways to write this, and you should we can write this in write this in terms of the kinematic viscosity, or the book also shows how to write it in terms of the volumetric flow rate and the mass flow rate. In fact, by accounting for, basically plugging in Q equals VA and so forth. So there's a number of ways to write this, but it does depend on D. And so you could see that we might be wanting to specify a pipe size that is either going to have laminar or turbulent flow in it. So we need a way of standardizing pipes. And so this nominal pipe size system, the NPS system, is a standard way to specify pipes. And so these are what I'll just very quickly say that these are the NPS, basically the indices. These are the outer diameters of these pipes. And then we have what's called a schedule. A schedule, either 40 or 80, or sometimes 120, sometimes 10, whatever NPS index we have. We also have a couple of different schedules. And the schedules are going to specify what the wall thickness and the inner diameter of the pipe are. These were initially set forth because we needed to have a system that specified the wall thickness such that we knew that the pipes would be strong enough to withhold certain pressures. And so we can we'll be using the Reynolds number and calculations to set for a certain velocity. We can then choose, given the type of fluid, we can then choose the diameter to get a particular Reynolds number to have either laminar or turbulent flow. And primarily we're going to be interested in the inner diameter, which is going to be what's important for the Reynolds number calculation, but also the wall thickness can be important in terms of the strength of the pipe. So once we determine an inner diameter, that might give us, for instance, an NPS index of 4, and then we would have to decide which of these schedules we would want to get the right wall thickness and outer diameter. So that's basically it for Chapter 10, and we will move on to Section 10.3. Thank you.